Okay, ladies and gentlemen, I will start a webcast. Welcome for joining. My name is Mark Dizay, and I will present this webcast about the validation of musculoskeletal models. Let me introduce the people who will help you through this webcast. As I said, my name is Mark Dizay, and I will be the presenter. Arne Kies, he is the host, and there are two people available for answering questions. The first is John Rasmussen, and the other one is Søren Tørholm Christensen, and they can help to answer questions both during and after the presentation. I will ask you to ask questions both during and after the presentation. You can do that by clicking the question mark in the right bottom of the screen, and then type your question in the question and answer panel. Please be sure that you send the question to both the host, the presenter, and the panelist, so everybody can see it here. And the panelists, they will try to answer your questions. And some questions will be kept until later, until I'm done with my webcast, and so that I will also try to answer questions orally. So once again, please make sure that you send the questions to both the host, the presenter, and the panelists. Before we continue, I would like to have this screen up because still some people have problems with sound. Of course, they cannot hear what I'm saying, so that's why they have to read this and for the instructions, to get instruction in order to get sound. So I will let this on the screen for a little while, and after that I will continue with the webcast. Okay, thank you very much. Let me try to introduce myself first. I'm working in the antibody research project here at the Aalborg University in Denmark, and at the moment I'm both affiliated with two institutes here: the Institute of Mechanical Engineering here at the Aalborg University in Denmark, and also another institute here is the Department of Health Science and Technology, a center called Center for Sensory Motor Interaction, also at the Aalborg University in Denmark. Validation of musculoskeletal models is it's a big issue at the moment, and it's very difficult to do. So I'm afraid that I will not give you real solutions, but I will present you some of my experiences and some of my advices how to do it. But of course, there might be other ways of doing it, and I hope we might get some discussions afterwards during the question and answer session. I will start my presentation with some definitions. Some of these definitions might be kind of understatements, but sometimes it's good to kind of confirm these understatements again. Then I will introduce three general ways of validating a model, and most of the time I will use giving some examples, both from the literature and also some examples which I've involved myself. And I will end the webcast with some concluding remarks. Some of the definitions I took from the book, The Biomechanics of the Musculoskeletal System, written by Benno Nick and Walter Herzog. I think that's a very good book, and there's a whole chapter is about modeling, and also they write about validation. The definition they give of a model is an attempt to represent reality, and normally there are two purposes why you want to build a model. And the first one is a more kind of fundamental research that people want to increase knowledge and insight about how the human body works, about the reality. It could be anything from humans, also animals. The second one I think is getting more and more important, and that is how people want to estimate or predict variables of interest. And those variables, they are normally very difficult or even impossible to measure experimentally. In 2002, I went to the World Congress of Biomechanics in Calgary, and there was a presentation by Christopher Vaughan. And he made a very clear distinction between modeling and simulation. He defines modeling as computer modeling. Computer modeling refers to the setting up of mathematical equations to describe the system of interest, the gathering of appropriate input data, and incorporation of these equations and data into a computer program. And a computer program that could, these equations could both be a computer program built from scratch, programming from scratch, or you could make use of some available tools which are already commercial or available, like Anybody or Sim or Live Model, for example. Simulation he defines then as computer simulations restricted to the mean the use of a validated computer model to carry out kind of experiments in carefully controlled conditions on a real-world system that has been modeled. I think theoretically this is a very nice distinction, although practically it's sometimes difficult, I think, to really make this distinction all the time. I think it's a good way of thinking about modeling and simulations anyway. Back to the book of from Benno Nick and Walter Herzog, they define validation as follows: that to validate a model can be defined as to provide evidence that the model is strong and powerful for the task that has been designed. When you see a definition like this, it kind of implies that you need to know the task. And it may seem very obvious, but at the moment, more and more now, people are working, different research groups are working on different things. So sometimes the model might have been developed for a different task, but it also could be used for another task. So you really have to define a task before you can actually validate a model, really. However, sometimes you might have a model without having a task already, some kind of general model. So then you need to, and it's really difficult to provide evidence that a model is strong and powerful, but you still could do some exercises that the model could be useful. But in general, I would say it is important that you need to know the task before you start to validate the model. Benno Nick and Walter Herzog, they wrote about 3 ways of validating a model. The first one is what they call direct measurements, and I will later on give 2 examples of that. And direct measurements you can use when you are able to measure the variable of interest. And I will later give an example of that. So if you then you compare the measure of interest, both the measured one, but also the estimated one from the model. This is a direct measurement, which is normally very difficult to do. Then the second type is what they call indirect measurements, and also we'll give 2 examples of that. Quite often it is impossible to measure the variable you are interested in. So what you then do is you measure variables which you can measure and which also the model can estimate. And then you compare those with each other, and then you kind of assume if they are if they look good, then also the measure you're interested in, which you cannot measure, will be okay. That sounds like a giant leap of faith, but in a lot of situations, this is really the only thing you can do. And then the third one, it's what I call trend measurements. And here the focus is on the prediction of trends. So that means if you change one variable in the model, then you look at how other variables changes due to that, and that you try to do the same thing you try to do experimentally. So the absolute values of your variables are of less interest than the prediction of trends. And I think this trend measurement, it should get more focus in the literature. There are some examples, but I think most people they look at the indirect measurements and the direct measurements. I will start with a classic example of the direct measurements from a group in Berlin, from Bergman and Heller, and led by Duda. And I think most of you might be familiar with a CD which was got together with the Journal of Biomechanics. It was called HIP 98, and they got two articles: hip contact forces and gait patterns from routine activities and musculoskeletal loading conditions at the hip during walking and stair climbing. And especially the latter one is a nice example of direct measurements. So what they did, they measured in vivo hip contact forces by means of instrumented hip prosthesis, which was implanted in patients. This hip prosthesis was supplied with strain gauges. A radio transmission, they could measure directly the hip contact forces. And then they also made a model of the leg, and then they compared different tasks, the estimated hip contact forces and the measured one with each other. Here an example of a task which I got from the paper in the Journal of Biomechanics in 2001. Here's a woman equipped with marker data and going up a stair, and the same and they measured the kinematics, but also these in vivo contact forces in real time. And then they had a model of the leg, which was based on inverse dynamics, which estimated the necessary muscle forces in order to produce that movement, and also they estimated the hip contact forces, and that they compared with each other. So here are two tasks. Here on the left, there's the task walking, and on the right is stair climbing. So let's first have a look at the walking here. The thick line, it's the calculated one, and the thin line here is the measured one with this instrumented hip prosthesis. And the one I just pointed out is the forces in the axial in the Z direction. So that looks rather good, and the same you can see here on the right one here. That's the one doing stair climbing. Again, the thick one is the calculated one, and the thin one is the measured one with the hip prosthesis. So if you look at the picture, this looks rather promising. However, So this is a direct measurement that indeed the hip contact forces are quite similar with the estimated contact forces from the model. However, this is not a guarantee that the underlying model is totally correct. As in principle, it is possible to get these estimated contact forces with different kind of muscle recruitment. But I think it's a very nice and direct way of doing it. And now I will show you another example of a direct measurement, which is about recumbent cycling. Basically, it could be normal cycling as well, doesn't really matter, the principle is the same. This has been done by Pamela de Jong and Kenneth Meyer from the University of Eindhoven. They made a model of the lower legs in recumbent position in the antibody modeling system. And I think this type of direct measurement of cycling is maybe not as well known as the other one by Bergman. So I will try to show you how it was done. First, have a look at the input in the model. The input in the model was based on measured kinematics, and the input in the model was strength torque. And to point out the crank torque, so is the input and not the pedal forces. However, the crank torque is based on the measured tangential pedal forces. So it's the tangential forces of both the right and the left leg together to create a moment around the crank. And these crank torque, this calculated crank torque based on the pedal forces are used as input. Then the model output is, among others, but the most important one we will focus on are the tangential pedal forces. And of course, the sum of these estimated tangential pedal forces should give, again, the crank torque. But it is not given how the division is between the left and the right leg. That is something the model has to figure out. Another model output is the radial pedal forces. And the radial pedal forces are, for the model, totally free. Because they do not create a moment around the crank. So basically the model can choose any kind of radial pedal forces in the model and still would fulfill the constraints of the crank torque. And then of course that model output has some muscle forces and activations as well. The measured variables are again the tangential pedal forces, but also the radial pedal forces, plus surface EMG measurements of the most important leg muscles. So what you then do is you compare the tangential pedal forces from the estimated ones with the measured ones, both from the tangential and the radial ones. Plus you can also have a look at the EMG measurements. So let's do that. Now let's first focus on this one here, this panel, where the tangential forces are presented both from the estimated one as the experiment. The dotted lines here are the experiments, and the line is the estimated one. And this is only on the tangential force on one leg. The sum on the left leg will be more or less the same, though it will have a phase shift of 180 degrees. And the sum of the left and the right leg estimated will give again the crank torque, which is input. However, the division, as I said before, between left and right is not given and be chosen freely by the model, which was based on inverse dynamics. So, and this looks quite okay, I would say. Oh, this was not what I wanted. let's have a look at this one here. These are the radial forces. And as I said before, the radial forces can be chosen totally freely by the model because they do not produce any moment around the crank, like the moment on the zero. But again here, the dotted lines are the experiments and the continuous line are the estimated radial forces. So again, this looks quite similar. However, you can see that in the estimated ones around here, there are some peaks you can see here, and and those peaks are located at the so-called dead points in the cycle. So the conclusion here is that the model, the muscle recruitment, the model chooses will result in radial forces and potential forces which are very close to the one we have measured. And I think that's a kind of strong indication that the model is working correctly. What you can see in the literature about cycling, modeling of cycle based on inverse dynamics, that quite often the input in the model is not the crank torque, but is directly the pedal forces. Which I think is a little bit of pity, because if you do it the way it's done here, you have a really nice way of showing that your model is valid or not. And here on the right side, there is also a comparison of EMG, both from the model and the estimated muscle activities in the model and the one obtained in experiments. The thick fat lines here and here, for example, these are the estimated one by the model, and the thin ones are the measured one on NMTs. So here it's only shown when a muscle is on or off, and you can see how much overlap there is. The Soleil looks very good, because Trichomonius has a problem here in the model. It turns out too late compared to the measurements. TDA's and Terra looks quite good, and the rest is quite good as well. But I think all these muscle activities together, it is these and the muscle and the motor control of these activities, they result in those radial forces on the pedal and the potential forces. And those you can get directly with measured ones, which I think is an interesting way of doing it. So then I go to an example of indirect measurements, which is based on the work which I have presented in the Journal of Mechanics, which is still in press at the moment. We've got again an inverse dynamics model. Maybe one remark on the side, that most of the examples here are based on modeling of inverse models. But basically the technology or the techniques of validation could also be used in forward models. It doesn't really matter. So this model is it's a mandible model with 24 hill-type muscles, where we got the data from a paper of Kolster and Van Eyden, and it's based on a CT scan of the normal face, it's a symmetric face of a 13-year-old male. The mandible was modeled with 4 degrees of freedom. And in this case, we are interested in the reaction forces in the jaw joint, in the temporal and mandibular joint. So that was really the output we were interested in. However, as far as we know, it's really impossible to measure these reaction forces in the jaw joint directly. So the only way evaluating this model is by using the indirect measurements. So what we did, we had a bite force measured clenching forces, biting at different positions in the mouth. And we tracked the jaw movement by a magnetic jaw tracker. There was a small magnet glued on the central incisors, which could measure the 3D precision. The measurements we did was surface EMG of the receiver and the temporalis. But on the other hand, also a lot of muscles which are very deep in the jaw, which you cannot measure with surface EMG. And for that purpose, we used some wire electrodes in order to measure the medial and the lateral pterygoids. Of course, there are more muscles involved in jaw movement, but you cannot measure everything. And we thought that these were the most important ones. So I don't know if you can see it on the picture, but there's a small wire going into the mouth here, intraorally, which was put into lateral pterygoid. And the medial pterygoid was a wire sitting here, which was put in behind the bone at the medial pterygoid. I'll show you one example where we used this force profile as input in the model. There was unilateral clenching at where this force transducer was placed at the left first premolar. And we asked the subject to increase the bite force to close to max, and then relax again. And this whole experiment took about 10 seconds. And then we used this bite force as input in the model, and then of course we estimated by again that is inverse dynamics model and optimization the muscle activities and compared it with processed EMG activities. So when you here you see the receiver, for example, on the left side, and here on the right side, and the red one is the simulation, and the blue dotted one is the EMG measurement, and they follow nicely with each other. What you also would like to do normally is try to quantify how good is your validation with each other. And that's why we have done, one way of doing it is simply to calculate the correlation coefficients between the normalized EMG envelopes and estimated muscle activities for each muscle and task. So the task I give you as an example is here with the red line around it, and especially the ones here. So of course this one here, they're very high correlation coefficients, and the total average is about 0.76. However, you see one here. If you look at like this in this table, it is a negative correlation coefficient, and that of course doesn't look very good, because it basically means that if your estimated muscle activity goes up, then the one you have measured in reality goes down. So that doesn't look very good. But if you only look at this number, and you would say, well, this is a bad result. But if you go back to the slide before, I go do that here, and I have a look here, because it was this graph here which showed this very this negative correlation coefficient. You can see that both the estimated and the measured EMG measurements are very low, with very low activity in this muscle for this unilateral clenching. And because we were mostly interested in the reaction forces in the jaw joint, one could argue, okay, these muscles are very low activated, so the importance of this negative correlation coefficient is very low. So it's not really an issue here. So my point here is that I think it's difficult to only have a look at numbers without looking at the kind of qualitative figures as well, and which I've showed in this case here. And then, here we have again this graph here which had this negative correlation coefficient. So I think the message here, only a number does not tell you the whole story, and I think you have to keep in mind when you do validation. So I'll give you another example of indirect measurements, a case called arm cramping, which has been done by a colleague of mine, Michael Woltz, together with Jonas Haar and Tina Messen, both at the Center for Sensory Motor Interaction. Background is that it is useful in rehabilitation, for example, of stroke patients, maybe to give well-defined movement instructions in order to exercise specific muscles or to avoid loading of pain in some muscles. So basically, the question was, how does muscle recruitment change with different arm positions? And when you look at this picture here, arm cranking can do in a lot of different ways. You can do it with elevated elbows, or you can do it with elbows very close to your body. So they try to validate the model by EMG measurements, and they used the so-called success ratio, which was introduced by a colleague of mine, Mark Thompson. Basically defined of the fraction of time points during a simulated movement where the predicted states, either on or off, matched the EMG measured on or off states. It's a kind of simple way of looking when trying to quantify when the muscle should be on or off in a model. And I think this is especially useful for evaluating cyclic movements like this arm cranking, but also the cycling or gait. The difficulty, though, is that you also need to you need to define when the EMG is on or off. So there are some thresholds there. There are some different algorithms available in the literature. I know a paper, for example, Paul Hodges has a whole paper about it. But it also means that if you use a different threshold or you use a different algorithm, that actually might change your results a bit. So I have here two examples here of the biceps brachii, for example, with elevated elbows, and here we see the thin line here is the measured EMG profile, and this red line here is the estimated muscle activity profile. And here you see kind of symbolized the blue one here. The blue line here can present when is the muscle on, and this one here presents when is the muscle off. The red line presents when the muscle is on or off in the estimation by anybody. So if you can then divide these times, you can calculate the so-called success ratio. And here, in this panel here, it's done the same, but then with the lowered elbows. And you can see that there's also already a difference between these two tasks. Anybody predicts that the muscle is longer on than it was in reality. So if you have a look at the numbers here with a high elbow position, with the elevated elbow position, and here we see the mean of the success ratio. They are pretty high numbers. It's only the triceps here in subject 4 that gives some problems. However, when you go to the lower the elbow, then suddenly one muscle here gives a very low value. So something did change either in the model or there was an experimental error. So this kind of indicates that the model changes its behavior between lowered elbow position compared to a higher elbow position. So there's something to look into. Probably it has something to do with how the deltoid changes moment arm in between these positions. I would like to give you the last example about trend measurements, and I go back to this recumbent cycling, which was done by Pamela de Jong and Kenneth Meyer from the University of Eindhoven. The final aim of their study was to find an optimal recumbent position in combination with an optimal cadence. And I think these trend measurements, they are good for comparing different designs configurations. And in this case, when you talk about cycling, you are interested in the position of the chair compared to the position, and could see how the overall energy consumption changes with these different designs and configurations. So the model should react the same with estimation than in reality in order to predict the right trends. And what they did, they measured oxygen consumption, and they estimated that for 3 different configurations, and they measured also for 3 different configurations. However, this was not without problems, because the trends they found in the simulations were kind of small differences that it could not be confirmed experimentally. And I think in general, one of the reasons is one of the challenges one has, that in a model you can change easily one parameter while all other parameters are kept constant. However, this is very difficult or maybe even impossible to do experimentally, especially when we talk about cycling. If you change one parameter, like the setup position, you will change all the parameters as well. So there are some issues there. Another thing one has to think about that quite often the real measurements also not a kind of gold standard. Especially when you measure oxygen during exercise, these are not very precise, and I think they could there's an error of 5% or something in this case, and especially when the changes you find in the simulation are very small, it might just be impossible to measure the changes experimentally, both because of the measurements are not precise enough, and also that you cannot keep your parameters constant as you can do in the simulation. Then some kind of last talk about experimental challenges, because as I said before, also there might be error in the models, and how you build the models, and the input parameters in the models. When you do a validation experiment, there are also a lot of experimental challenges, and I will give you one example. For example, people are interested in measure tendon forces in vivo, which would be very nice if that was possible in reality, because then you would be able to do a direct comparison, a direct measurement with measured tendon force with an estimated tendon force, for example, the Achilles tendon. Paavo Komi in Finland, he already introduced a long time ago these buckle transducers in Achilles tendon, which is quite of an invasive procedure, but he did some studies with that. It looks like this. So it's a buckle transducer based on skin gauges, and if the force in the tendon increases, then this crossbar here will change shape and it can be measured. The first problem we have already is the calibration of this device, because you cannot calibrate it offline or in another tissue, because every tendon has its own the tendon together with the buckle transducer has its own behavior, which is unique behavior. So you need to calibrate it on spot in a subject. This example is from a PhD thesis of Michael Voigt already in 1994. What he did, he tried to test his buckle transducer in, as can be seen here. So the buckle transducer is sitting here, and an extensometer is sitting here in a material testing machine. It turns out that these buckle transducers changes characteristics as a function of the frequency of loading. But the conclusion is here is actually it's very difficult already with this buckle transducer to get really reliable tendon forces, which could be shown in an in vitro dynamic test, as in this figure here. Moreover, later on, also Paavo Komi, he introduced the optical fiber, which could be it's a little bit less invasive than his buckle transducer, still somewhat invasive, in order also to measure Achilles tendon forces. So that has been done, and for example, here we see an example which was obtained during Gates. We have here the optic fiber output, the ankle joint angle, and the EMT in both the soleus and the tibialis anterior. That it looks quite nice. However, it has been shown that this output of the optical fiber is really quite insensitive of the force in the tendon, which is not a good thing. But it's very sensitive of bending due to the skin moving during movement. So also here, the obtained values in the optical fiber are quite questionable. So some remarks here in the end. I think when you do a validation, a combination of quantitative and qualitative methods is desirable. Both because I think only numbers does not tell you the whole story, as I showed in this memorable model. And just looking at things in a quantitative way is also desirable. Also should have a critical look at the experimental methods to do. I don't really think that there exists a golden standard. Also in some of these measuring tendon forces, there are also EMG measurements as you look at what challenges involved there. And as a paradox, the reason for developing models is normally often because it's very difficult or even impossible to obtain experimental data, and that's why I want a model in order to get these information. And I think that trend measurements will make more important, especially when models are used for comparing different designs or different things with each other. Then one really has to focus on the trends if the model reacts the same way on a change in distance as the subject do in reality. And I think this trend measurement this should be more important than it has done before. And I would like to give you a quote, kind of a concluding remark, which was written by Langenbach and Hannan in the Archives of Oral Biology. Whatever arguments can be made regarding validity, we suggest that such models are perhaps best considered as working hypotheses. In circumstances, a model's use of plausible input information and its demonstration of any trends, association, and consequences which support such observations as are available simply strengthens or weakens the case for the hypothesis model as a conceptual framework. And I think this is the kind of good way of looking at things, as looking at a model as a hypothesis. So this is what I had to say here in the webcast. And now we can have some questions, and I will try to answer them. I look at the host here. I have